I'm here with Professor Matilde Marcolli, a renowned mathematician, mathematical physicist, linguist, prolific author, and professor of mathematics and computational science at Caltech. Marcolli has worked with luminaries such as Yuri Manin, Michael Atiyah, and Noam Chomsky, receiving honors from institutions around the globe. Would you like to speak at all about your history involving your work, your experiences with Chomsky or Manin? Really just.
Yeah, well, it's kind of a long story,
Mm.
but I guess most of my work over the years has been, of course, at the interface between mathematics and theoretical physics. I started out my sort of, in a sense, academic life as a student. My first studying theoretical physics in Italy, in Milan, and then I got also PhD in math at the University of Chicago, and I kind of shifted between as well as a student in theoretical physics. I was interested in gauge theories, which are the theories of elementary particle interaction forces, and uh, and then I sort of switched to mathematics where this same type of equations like Young-Mills equation that govern the elementary particles in physics, they also provide invariants that distinguish between manifolds, so spaces in especially in dimension 4 in mathematics. So they allow you to distinguish. It's kind of an interesting concept. You can tell apart four-dimensional spaces by the way that elementary particles would behave on them.
Yeah.
So that was my first area of research. And my first job after the getting my PhD in math in Chicago was as a postdoc in mathematics at MIT, and I was still working on these things. It was my main research. But like over the years, I had an interest in linguistics, which came from the fact that my original training before I became a physics student was in classics. So I spent like many years of my life, reading ancient Greek and this kind of stuff. And of course, I had a sort of a very classical interest in linguistics, this sort of like very classical philology, of ancient languages, that sort of gradually, got modernized into an actual interest for linguistics in itself. And so while I was a postdoc at MIT, out of curiosity, I sort of sat for a while in Noam Chomsky's linguistics class, and it was at the time it was in the late 90s, and so this model of minimalism that was just being developed in the early 90s. I was talking about these things, and at the time I actually felt that I wasn't really understanding all that much of what was going on there. But I still had at the back of my mind this sort of feeling that there was something that sounded like familiar to my mind as a mathematician, but I didn't really make the connection at that time between these things. So it kind of sat there at the back of my mind for many years. But then, so after I finished my job at MIT, I worked for a few years at a research institute in mathematics in Germany, the Max Planck Institute. And that's where I actually started my collaboration with Yuri Manin, who's unfortunately died recently, but it was a very famous Russian mathematician. Had also an interest in theoretical physics. And there's another funny story about that, in the sense that when I was a physics student in Italy, and I initially wanted to be a nuclear physicist, and so we were sort of this group of young people wanting to be nuclear physicists, and we were sort of trying to look cool and read this Russian journal of nuclear physics, which is called Yadarnaya Fizika. And so I was spending time in the library, showing off how cool I was by reading this this stuff. And I ran into this paper that was published in this nuclear physics journal, Russian nuclear physics journal, but it was by Manin and Drimfeld, another very famous Russian mathematician, on like instantons, which is like the mathematical theory of Yang-Mills interactions. That's why it was sort of published in a nuclear physics journal. And I looked at that and said, "Oh wow, this is like the most beautiful thing I've seen," and that sort of had an influence on my gradually shifting from nuclear physics to theoretical physics and to mathematics, and so like a few years down the line, I ended up working at Max Planck Institute, and in the meantime, Manin had been also moving out of Russia, and first, was a professor at MIT, and then, at the Max Planck Institute, where he became the director. And so we started working together. And so this is another of these sort of strange coincidences of life, like my sitting in Norm's class of linguistics at MIT. I was a postdoc, and then ended up working together on this merge theory many years later. So that's yeah. So, and in those years that I spent at the Max Planck Institute, I started several other collaborations. One of them was with Alain Connes, another famous French mathematician. And one of the things we worked on was also related to physics, and in particular related to the problem of renormalization in quantum field theory, where the quantum field theory in its history has been plagued by this problem of unwanted infinities. So you have this, you try to compute quantum corrections as order by order in what they call the loop number expansion, perturbative expansion. And these corrections are parameterized by these convenient bookkeeping devices, which are called Feynman graphs. And they sort of describe the fact that when particles interact, they kind of generate virtual particles that are generated and created and annihilated between interacting fields. And when you want to compute things like expectation values, you have to average over all these possibilities of things that happen in the interaction process. And very often when you try to do that, you end up with something meaningless, like some divergent stuff that makes no sense. And so there is this problem of trying to extract physically meaningful values in a way that's consistent with the way that these substructures occur inside larger structures. The structure here means these Feynman graphs. Okay. And so this is known as the problem of renormalization in physics. There are recipes, which means like formulae that you apply and somehow they magically work. But like for a long time, there was no like actual conceptual, explanation for that. And then Kohn and another German physicist, Kramer, they actually found out that there's a very nice algebraic explanation for why this phenomenon works. And Kohn and I sort of put it for further, develop this algebraic formalism behind this renormalization process. And this is kind of like another ingredient that played in an interesting way in all these stories, because I did this work on this renormalization problem in physics. And then, because I was collaborating with Manin at the same time, and he was also interested in problems in the theory of computation and in logic. He has a famous book in logic that he wrote. And he kind of used some of the work that I've done with quantum renormalization to try to formulate a similar problem of infinities about like undecidable problems or non-computable functions, and see that there is a similarity where sometimes you can kind of extract a meaningful, like computable function out of a non-computable, non-decidable function. And he formulated that, again, as a renormalization problem in a similar form as the quantum field theory one. And that's sort of like an intermediate step between the thing that I was doing with the physics side and what I've been working on with Norm and Bob Berwick now on linguistics aspect, because at some point, as I was doing these things, all of a sudden I had this flashback, to what I was hearing Ron say in this class of minimalism, and I sort of, that okay, now it starts to make more sense. There is actually a very clear similarity where you're dealing with another kind of generative process or combinatorial structures, which now are like the syntactic objects that you just talk about in linguistics. And you also have a similar problem of like consistently assigning meaningful values to these structures in a way that is compatible with substructures. And this is the whole idea of parsing in linguistics. And so in a sense, this idea of generating structures and at the same time having a kind of generative process, which at the same time has to act as a parser, is very similar to the conceptual setting that you have in quantum field theory, where you have like this generative process that give you all these interactions of particles in the form of Feynman diagrams, and you have this problem of extracting consistently meaningful physical values from them. And so I realized that, okay, this algebraic formalism that worked and that also, Manin has shown can be applied to other settings that are not physics, like theory of computation and so on, is naturally the way that one could think about this linguistic setting. And so, I actually kind of, started trying to write out some notes about that. I passed them on to Bob, he passed them on to Noam, and then we started discussing this thing together, and that's how we ended up doing this work. So that's kind of like, a kind of very long story, but I think it sort of illustrates the fact that there's a lot of intertwined, paths that happen because you sort of are in the right place at the right time by some completely random reasons.
With the right experience, yeah. So you are very multidisciplinary academic. You've got a history in classics, in linguistics, in quantum physics, in theoretical physics, and the interplay that all of these things have is incredible. So is there any aspect that you think within your work that multidisciplinarian mindset has allowed you to see things that you might not have otherwise seen?
Yeah, no, certainly. I mean, I have to say that most of the time, mathematics, by its own nature and history, tends to be a very highly specialized field, and it's split up in like very, very small communities that usually are high, have a high degree of inbreeding, and they kind of they focus on some particular problems that are very, very subculture specific. And this is in the nature of things, because sometimes some of these main open problems in mathematics, they require an enormously focused kind of approach to be tackled. On the other hand, putting all the focus in mathematics into this type of research, I think misses out on a lot of opportunities that come from actually seeing connections between different areas. And in that sense, I'm more, as my scientific upbringing, I'm sort of more in the Russian style that tended to have a lot more of interaction across different subfields in mathematics and across mathematics and physics. And so I sort of kind of benefited a lot from keeping that perspective. And of course, it turns out in the end that also the interest that I had in other fields that outside of mathematics and physics that ended up playing a role. I'm also kind of collaborating with neuroscientists and trying to come up with maybe interesting geometric ways of seeing some of the questions in neuroscience. And so I think there's a lot of it's sort of natural that when you encounter something that is like a very fundamental conceptual structure in some setting, you're likely to encounter it over and over again in other settings, because you are sort of describing in some sense what we actually like to call a fundamental law of nature. What is a fundamental law of nature? It is exactly a kind of conceptual scaffolding that is likely to play a role in a lot of different settings.
Lightning sees the fastest way to ground, and in that sense, the most useful structures will happen over and over again because they survive beyond less useful structures.
Yeah.
Within your work, there's also poems that you've written, articles, and plays that you've actually written. Would you like to speak at all on your experience with that?
Yeah. So of course, no, like everything in the world, no, there's nothing is all no black or white, no. So everything has its dark side, and of course the scientific community has a lot of dark sides, and you inevitably have to deal with them as you work as a scientist. And in some sense, there are different attitudes that one can have about that. One is to, well, basically try to ignore everything that's happening, and try to like shelter yourself as much as possible from the all the ugliness that exists inevitably. And I don't think that's a very good strategy, because okay, it might be okay as a survival strategy for at the individual level, but it's sort of looking the other way is like not helpful in trying to make the community better for all the people involved, because okay, you might survive, but it doesn't if there are systemic issues in the community, they will remain there, and it will not help other people. So I've kind of been using part of these other forms of expression, like writing. Yeah, for example, I wrote a theater play some years ago that was represented by the Caltech Theater, and this was focused on some of these less pleasant aspects of the scientific community, in particular the mathematical community, that have a lot to do with pathological narcissism, and the sort of damaging effect that it has on other people in the field, especially of course very often the receiving end of these things are more likely to be people that already belong to like underrepresented group in science. So there's a lot of these dynamics that one faces over and over again. And so I use some of these things like poetry or theater as a way to describe some of these things. I mean, theater, I think, is an especially powerful form of expression. From the very early days I mean, I'm trained in the Greek literature, so in the very early days of Greek drama is a way to actually put out there on the stage something that has to do with the drama of our human existence, and being able to like look at it at a distance. That's why the chorus wears masks, and we have and everything is sort of displaced in a way that it can be looked at like from a distance in some sense.
The suspension of disbelief.
There is of course in theater
seeing emotional truth,
a kind of suspension of disbelief, but it is also this very direct connection at the same time, right? So you can make things happen on stage that involve you but don't involve you at the same time. And so I like the use of the theater as a form of expression in that way, in that tradition of the sort of high drama, or the classics, the Greek drama, or and so I might return to that in the future. I think it's a very good form for discussing things.
And historically, in the ancient Greek example, you had plays like Trojan Women and Agamemnon, which brought forward that more populist narrative rather than one that would be generally accepted by the ruling class. You've written on anarchism as well. Would you say that the mathematics and the physics informs the political beliefs, or is it more your experiences outside of the scientific fields?
It's a good question. It's an interesting combination of these things. I mean, so I grew up. I mean, I was a child in Italy in the 1970s, and that was a very peculiar historical moment. So Italy was, well, it's fair to say, close to something resembling a civil war at the time. the danger of fascists trying to regain power was extremely real and extremely part of your everyday life. In the span of 10 years, there were 36 bombing of trains, right, and additional events of that nature. And of course, the radical left felt that there was no way. So I mean, premise to this, the Italian constitution that was written immediately after the end of the war, at the end of this big anti-fascist resistance movement that happened during the war, was is explicitly saying that fascism is illegal, that any attempt to reform fascism is illegal, and so on. But it's a good example of the fact that you cannot just legislate fascism out of existence. It doesn't work because, well, obviously you can have a law, but who's going to enforce that law? And if the that are in charge of enforcing that law are, well, the ones who are most likely to side with, it's not going to help. And okay, so that's part of where my radical political stand is coming from, and in part it also evolved in my experience in science, because I realized through exactly this kind of problems that you see in the scientific community, that really, so in a sense I was brought up like more a traditional Marxist, but with all this sort of class reductionism, that the problem is that you have to solve the class war problem and everything else will fall into place. But you see sometimes that power is the problem. And of course, economic power is one very strong manifestation of the power, but it's hierarchy and power in itself that is the problem. And that's why I think of myself more as an anarchist than as a communist, sort of kind of Kropotkin type anarcho-communist, but the anarchist component is become much more prevalent in my political stand over the years, precisely because I come more and more across this issue that dismantling structures of power is the most important thing.
Fantastic. Thank you so much. We're going to take a short break, and then we're going to have some questions from the students in the room. Again, thank you for doing this interview. It's incredibly enlightening.